Right. So I hope like my audio is clear. If not, like please let me know. So yeah, this is your week 3 of your Thanks, Premdeep. So yeah, so this is your week 3 problem solving session. So today we'll be discussing about the orbital and spin angular momentum algebra and the related concepts. So yeah, so again, this is going to be very essential for you because moving on from this point, so whatever new topics or the rest of the following topics that you will be finding in your way throughout this rest of the course in your advanced quantum mechanics with applications. So you will see the extensive applications of all this angular momentum concepts. So yeah, and yeah, you will be always able to get them in your way whenever you do the following topics that will be coming in your way. So yeah, and also I think you can able to see your lecture videos by the instructor. So which is I think you can able to access from your portal. So if any issues, please let us know, and also assignments. So please try to finish them before the due date. And yeah, so yeah, it's already like I think we are moving or we are going closer to the halfway of your NPTEL course. So yeah, I hope you are doing well. If any problem, so just let us know here. Like we can discuss and we can try to resolve. So um, yeah, so we'll start off with some like I mean the introduction of the anglo momentum algebra in quantum mechanics. So somehow or the other, like you might also know them from your earlier quantum mechanics course if you had maybe from quantum mechanics course level 1 sort of. So yeah, but we'll go through again from the from the scratch. We'll see how we'll also do some related problems, and that will essentially will try to make you familiar with this kind of algebra related to angular momentum in quantum mechanics, and which will be thoroughly used in your upcoming topics. So yeah, um, so we'll start off with some we will orbital angular momentum. Then we'll talk about a little bit about spin angular momentum as well. So um, yeah, so orbital angular momentum. So if you know from your uh, um, uh, Yeah, so orbital angular momentum. So you know from your classical dynamics course. So this is something uh, uh, defined to be the cross product of position and momentum vectors. So again, so from canonical quantizations or the first principle of quantizations, we know like we in quantum mechanics we promote them to operators. So now so this angular momentum like classically how we used to define. So now this will become operator. So this is your position operator and your momentum operator. And yeah, so and if you know the momentum operator is this is given to be uh, minus I h bar grad operator, right? So yeah, so now so and yeah, and this is your position operator. So so in quantum mechanics you treat them as operators, and accordingly you will also have here something minus I h bar, then y operator will be just y, and then you have uh, the differential operator with respect to z for the momentum, and then you have z uh, del y, right? So yeah, so this is how you can write in quantum mechanics. So so this is your Lx, Ly, and Lz. So yeah, uh, so now if you see, this is your how this operator it is written here. So this is your Cartesian form. So so this is your Cartesian form, because like when you are dealing with simply xyz coordinates, so this will be your simply Cartesian form. And when you go to spherical coordinates, and which is again quite significant when we study in spherical polar coordinates, because most of the things that fall most of the things you will find that they will fall very easily to understand or to solve the algebra in a in a more uh, uh, what do you say, like in a more concise way. You can get the final form of the various things, like the eigenstates or the eigenvalues. All these things you can uh, get it when if you solve or if you deal with spherical polar coordinates, particularly when you have spherical symmetry in the system. So like for example, when you try to learn about hydrogen atom system in quantum mechanics, or some sort of like Coulombic potential, or some sort of potential that involves theta or phi symmetry. So in those cases, it becomes very easier to deal with spherical coordinates. So so in spherical coordinates, like here, as you can see here, I mean, you know, so you have to go from x, y, z to uh, r theta phi system. So um, so if you remember, like these are something, r sine theta, cos theta. So this transformation, when you do, uh, so this will be phi, cos phi, and this will be, so these things you know already very well. So yeah, and then if you also use because here if you see, the operators are defined to be grad operator or the differential operators. So for grad operator also, like if you uh, see or like in spherical coordinate, uh, so from here, like in spherical coordinate system, again, you would probably, you would know this, like it's somehow like from your mathematical course, like in spherical coordinate. I think this is something can be defined to be some radial unit of vector. Then you have something theta unit vector over r, and then I think this is, yeah, yeah. So then yeah, when you will use this, and again this r and theta and phi can be expressed in terms of x, y, z, and yeah, then they can be expressed in terms of like I cap, j cap, k cap components, like the components of x, y, z, ordinary x, y, z Cartesian unit vectors. So and then so when you have all of them, and when you put again in the definition of Lx, Ly, and Lz, you will find exactly what Lx can be in terms of r theta phi. So this is how lx, ly, and lz operator can be derived. So yeah, and then again for L square you can take like the R cross P. If you do it twice, then you get this L square expression. So again, yeah, so this LXLY LZ, or the L square, like which you see here, like in terms of R theta phi, may seem little I mean a very complicated looking operator, but yeah, it becomes very important when you try to use them in certain quantum systems, like which has spherical symmetry, and it becomes very easy, and yeah, and becomes very, particularly the results you will get from there, it will be very easy to understand and interpret. So yeah, we'll see ahead like how this can be useful. uh, yeah, so this is on the idea about the operators, how you can express them in quantum mechanics for orbital angular momentum, and then we'll talk about their algebra. Uh, so so this is the angular momentum algebra. So when yeah, so what happens, like if you take lx, ly, and if you take the commutator, so you get something non-zero, and that interestingly becomes equal to the lz operator. So and if you do ly, lz, you get lx, and also if you do lz or lz with lx, then you get ly. So they have a like uh, right. Just a minute. Yeah. So they have a basically cyclic commutation algebra. Uh, L cross L, you get L. So cyclic commutation, like here I mean cyclic commutation algebra. So like when you do LXLY, you get LZ, and when you do LZ LX, you get LY, and also when you do LY LZ, so you get LX. So it's like cyclically, like it permutes. But if you see, if you do the commutation of L square with LX, or any of the other angular momentum component like Ly or Lz with L square, you get zero, which means that if any certain operators commute with each other, then it tells that they can be simultaneously measured. They can be measured with arbitrary accuracy, and they must share a common eigenstate, and the eigenstate, let's say, is given by Lm. Here in this case, it is given by uh, ket Lm. So Lm are the two quantum numbers. So in which I mean this quantum system must depend on. So if you see, like this L, um, right. So if you so this L is can be known as orbital quantum number, and M is sometimes referred to as uh, azimuthal quantum number. So again, like if you remember, like I mean, uh, uh, yeah. Okay. So in order to like to understand about this eigenstates. Look, I mean, like going forward, like we'll do a one related problem. We'll see how this LM angular momentum, this eigenstate can be the can be expressed in terms of this expressions. So this is like for, let's say, or if I assume, like if you have seen hydrogen atom system, so hydrogen atom system, like the potential is something like I mean it for something potential of this form 1 over r. So this Coulombic type potential, if you consider any quantum system like the hydrogen atom, so in that case, like you have a spherical symmetric. So for spherical symmetric systems, so you will find that like they have a some special type of eigenfunctions which are known as the spherical harmonics. So this Lm, so this Lm is written down in some as some function of theta and phi, including this L and M integer, L and M integers, which are basically the quantum numbers, and this is known to be as spherical harmonics. So again, like if you have some, let's say, if you have some kind of this kind of potential with you, and you start off with your Schrodinger equation. So from here, if you like start off with your Schrodinger equation, and then this psi will break down into two parts, like something as radial part and something as the uh, spherical harmonic. So if you solve this Schrodinger equation, so and this spherical harmonic, this part spherical harmonics, and this is something precisely the same eigenfunction for L square and Lz. So it turns out that this also becomes the eigenfunction for L square and Lz. So if you take this ylm and operate L square, so L square, as we have seen here, so this is your L square. So if you take this L square and you operate this on ylm, so again you will find ylm with some like uh, some eigenvalues. So and these eigenvalues are given as this, and the same thing also happens with uh, Lz operator. So here also, if you operate the Lz on this spherical harmonics, so again you will get the same thing back again with this scale factor, which is basically your eigenvalue. So yeah, then yeah, so what I mean to say here is, like, suppose if you uh, take this L square, so let's say right over here, so let's say this depends on psi and lm. So if I take L square operator, uh, yeah, and if I operate this on nlm, so nlm depends on all r, theta and phi, all the coordinates, and so this L square basically means r n l r y ln theta phi, and then uh, so this L square, if you see the expression of L square operator right here, so it purely has only theta dependence and phi dependence. So it means, so when if this acts on this whole thing, it will only be important when what happens if this will go through ylm, because rnl will be just simply like a constant, because L square doesn't have any r variable in its expression. So if you do this algebra, so you will find out, like on the right hand side, you will find L plus L1 h bar square. Then the whole thing you will find psi NLL, r theta and phi. So yeah, and also if you see this expression very closely, this expression has some constant. So to get this detailed expression, you have to solve the Schrodinger equation thoroughly. Then you will get this the exact expression. So and when you do that, like you will find some constant, which is basically some normalization constant. So this is the norm part of the expression of the eigenfunction. And uh, so yeah, so these are your, remember, this is eigenfunction. So right, and this PLM cos theta, which is given right here, so this is something known as uh, uh, associated Legendre polynomial. So these are some special polynomial. Again, this is something purely mathematical stuff. So which like yeah, again, I hope you have come across some special polynomials in your mathematical courses. So this is just exactly that. So Legendre polynomials are one of those special class of polynomials that becomes the solution of the spherical potential type quantum system, including the factor of this exponential im phi. So yeah, then right. So and if you see, the m has negative value and also has some positive value. So L and M are purely quantum numbers. So L M are quantum numbers where yeah, where the value of ml uh, or m is basically decided by the value of l. So minus l to yeah, it will go like minus l, minus l plus 1, minus l plus 2, to plus l. So yeah, so this is all, I think, yeah. And if you take their normalization, if you take the overlap integral, so you will get delta functions, because we already have taken account of the normalization factor. So this is some some prior information which you need to keep. So yeah, um, and all of this detailed expression, this huge looking expression, you need not to bother about much about it, like how we can get them. So definitely it's a very long task, and you have to work out from the beginning, from Schrodinger equation. You have to work out the solutions in detail, and then you can get them. But some important ideas, like there are quantum numbers, there are two important quantum numbers when you are dealing with orbital angular momentum in quantum mechanics, which are L and M. And there are something spherical harmonics, which are basically the eigen states or eigen function of the L square and Lz. So uh, so has it, I mean, everything is fine with you, or any doubt or anything not clear, any kind of problem, or any kind of silly question if you have, or anything like any small or basic thing also, if you missed it, or something not understood at all, or so, is everything fine with you, all of you, like uh, okay, it's fine. So yeah, and okay, so if you are not having any uh, a question right here, then let me tell you quickly. So again, talking about angular momentum, so there is one various, there is one particularly sort of very mysterious like uh, concept behind when you talk about quantum mechanics. It is spin. So which again, like if you see the behavior of spin, or the mathematical the mathematical construction, or the mathematical structure of this physical observable when we try to study. So you will find that this exactly takes the form, or rather it's identical. The mathematical structure is or the mathematical structure, or the algebra, or the identity will give you exactly same as orbital quantum number. This spin angular momentum follows, or something, it follows exactly identical to that of orbital angular momentum mathematical form or structure. So uh, and yeah so with that, like, we have concluded that it is the property of spin, or the spin, which is like I mean the point when we have found out. So we're going back to the Stern-Zerlach experiment. So if you remember, is something also I think discussed in this course as well at the beginning. So talking about that spin, because of which you had different space quantization, and so on the screen you get some it is some sort of a scattering experiment you perform, like in Stern-Zerlach experiment, and then you get distinct, or some segregated lines. So this lines basically gives you the uh, dependency of a different characteristic in quantum system, which is known as spin. And when you try to study the mathematical identity behind this physical observable, you find that it exactly follows follows the structure or the form of orbital quantum number, which we just discussed right here. So with that, um, yeah, keeping that in mind, like, we can construct the same thing back again. So you will have uh, um, I mean so let me just write it. It follows uh, exactly identical uh, identical mathematical uh, structure of orbital angular momentum. Yeah. So again here, if we write the spin states by S and ms, so just like how we had L and M, or ML. So same way we can write here the eigenstates here. Or before that eigenstates, like, as we have seen, or we have talked about algebra. So here also algebra in spin angular momentum will again be given in the same way. Sx, xy, if are the x and y components of the spin spin operators, then this will be equal to the sz. And same way you will have this cyclic commutation rule here as well. And then you also have uh, uh, s square with sx, or any of the other component of the spin angular momentum, you will have 0. And then again this tells you that, like, you can write it as uh, same eigenstates. So s square and sz must have same uh, uh, so s square and s square and SZ also have same eigensets. So they commute. So S square will commute with any of the component of the spin angular momentum, just like how we have seen for the orbital angular momentum. And again, same here also, you will find these common eigenstates to be of something given as S and MS, and then it will have these eigenvalues. So the same thing that we have seen for orbital angular momentum. Yeah, so this is what I wanted to uh, tell you beforehand before we start doing any like any problem related stuff here. So this is something enough to like go forward in order to solve any any questions or anything or any new topic also. Like when we talk about spin, you will see that like this will come whole through, I mean, every topics. Like if you talk about nuclear magnetic resonances, or if you talk about quantum information as well, the qubits, the system of qubits which you will learn, or everywhere, like you are bound to get all these things again and again repeatedly at every point ahead, like when you will do. So systems is something very important, and all the modern technology or the yeah all the modern technology that you see, the new scientific developments, like all go through this understanding of spins, and it is very essential, whether it's quantum computing or any like any other stuff in like a condensed matter system, or anything in superconductor or anywhere. Like I mean, this becomes the like pedestal to all the other topics. So yeah, so this is just a very basic definitions behind this. So any question or anything not clear? Uh, okay, so anyone else, if not clear with anything which I said here, or anything additional if they want to add, or something if I missed it, or something properly not understood, like all of you can speak. And uh, okay, so we'll start off with this basic relation of this commutation. So as I was talking about LXLY, when they commute, they have a cyclic commutation relation. So yeah, so LXLY it gives you when you take the commutation, it gives you the LZ operator. So how is it? Like we can see. Um, so if LXLY, from the definition of Lx, we know the x component of angular momentum is basically ypx, and these are all operators. Remember, because in quantum mechanics, that is what. Uh, so this will be ypz, right, and zpy. So this is Lx, and similarly you have Ly. So this will be px minus xpz. Okay. Then you have now you can just separate out the each commutators. So meaning I can group them in the following way. So y pz with z px, then I have minus here, then z py with or let's take ypz itself, uh, ypz with xpz, and you have zpy with zpx, then you have this will become plus, so zpy with xpz, right. uh, yeah, and with that you and I think like you are all already also familiar with one of the most fundamental commutation relation in quantum mechanics, is the commutation of x and px, the position and momentum, which basically gives you IH bar. So yeah, so this goes back to your uncertainty relation and all these things. So yeah, so it's likewise you can also write y py and uh, z pz. So that is also IH bar, and y and px will come out because yeah. So if you take the any yeah, if you take the same component of position and momentum, so they never commute. So basically you cannot simultaneously measure them. But if you take different components of either position or momentum, then certainly they will commute and they have the yeah, then you can simultaneously measure them. um, so using this right here, so what I can do here, so since as I said, so y and px, so they basically commute. So like what I can do, I can write the let's say about this term, I can write this as y um, pz and z, keeping it inside, and I can pull out px outside, and the same thing I can do for y pz and x and pz. Same thing I can do z py and z px, and then z py and x and pz. So now I can like uh, use this commutation relations here. So if you see, this will give me IH bar. So I will get y uh, rather it will give minus IH bar px. Then from here I will get 0, because pz with x is 0. They are different components, and the same from the next term as well, I have 0. And then the last term will give me uh, uh, yeah, the last term will again give me minus IH bar. So no, the last term uh, uh, just let me check if there's something, if I uh, ZPY.
Sir,
Uh,
uh, in the in the above line,
uh,
like the above, you have written minus of z uh, py comma z p. It's
uh,
px or pz.
that is PZ. Uh,
Sir, last second last line.
this line, right?
Yes, sir. Yes,
Haha.
sir.
Haha, right. So this is what you are telling. This is
I
uh,
am asking
huh.
the first term zpy comma zpx or pz.
This is ZPX.
Okay, okay.
Yeah. So any problem here?
Yes. I thought here it should be pz.
It would be PZ because I am taking uh, this term with this term. So I have ZPY here and I have ZPX here. So I'm just like grouping these two terms right here. So like so
Oh,
that is
okay, sir. Okay.
why I have written ZPX. And yeah, if I group the last two terms ZPY and XPZ, so this will give me this. Uh, yeah, this will give me uh, right. And then Y and PX. Yeah, okay, okay, yeah. So last term, so maybe I should not group. Yeah, yeah, fine. So last term, what I can write. So if you see, I have PY. I can take PY and Z and PZ uh, with X. So yeah, so now like if you see, I have to figure out like in each of these four terms where I will have this kind of pairs X and PX. So or Y or PY or Z and PY. So if you see like from the first term I can get a pair of ZPZ. Then I can get a uh, similar type of pair like right over here, uh, ZPZ again. So and rest of the places you will see that like I cannot have such XPX or YPY or ZPZ pair. And then if you solve them, like you will find they will go to zero. So yeah, so again, so if you see, this will give me plus IH bar PYX. So then this essentially will become, if I write down here, IH bar uh, XPY minus YPX. So, and this is what your IH bar LZ. So yeah, so I think now it is clear. So is it fine right now? Okay. So anybody else like any at anywhere, if uh, not clear anything you didn't follow, please let me know. Yeah, so this is how you can also try to check what you will find if you take the commutation of Ly and Lz. You will get IH bar Lx. And same way, when you do Lz and Lx, you will get IH bar Ly. So the same way you have to do that, and there also you will be using this fundamental commutation relation, and with that you can also check the other cyclic commutation parts. Uh, so yeah, right. Then here we'll talk about something about ladder operators. So yeah, if there is no question anymore, we can go forward, or anything if you want to ask, like, please let me know. So okay, so just like, if you remember, even we have discussed it last week about the ladder operators, but we have discussed in quantum harmonic oscillator systems. But in angular momentum as well, if you see in quantum mechanics, we define something as ladder operators. Uh, so which is given by L plus operator and L minus, and it has the same job, like, as we have seen previously in harmonic oscillator. So L plus operator, it raises the uh, some angular momentum state to the next level, to the next succeeding level up, and L minus brings down the quantum eigenstate or some quantum state to the uh, to one state lower. So basically, if you so as we are talking about orbital angular momentum, so orbital angular momentum, we deal with this L and M states. So uh, uh, if you operate L plus, so it will take you up to L M plus one, and if you say L minus, so it will bring you down to L M minus one. And how this L plus is defined. So L plus is defined to be the Lx plus I Ly, and L minus is defined to be Lx minus I Ly. So if you define them in this uh, following way, then only you can satisfy this uh, lowering, or uh, if you define L minus in this way, and only then you will find that it can do this type of job, where you will have Lm, and acting L minus, which is defined to be this, then it can only bring it down to one step lower. So the same way, if you define L plus, and only then L plus can take Lm to Lm plus one. So yeah, so this is the how ladder operators are uh, given in context of uh, orbital angular momentum. So just like how we have seen ladder operators, how they work in harmonic oscillator previously. So again, to solve this commutation relation right here, we have uh, so we have to prove this, right? So Lz and L plus commutation. So if we write here Lz and L plus, so this is Lz, Lx plus I Ly. So this is Lz Lx plus I Lz Ly, right? So then, from LZLX, from the cyclic commutation, which we have already seen before, and also try to prove one of them. So we'll have IH bar Ly here, and then plus I, and again here LZLY. So this will give us minus IH bar LX, and then if I properly arrange it, you will see it can be written down H bar Lx plus ILy. and this is precisely what H L plus or the L plus is what defined to be this. So yeah, this right here. Yeah, the same way, like you can also check one more case. You will have Lz L minus to be minus of H bar L minus. So you can check yourself the same thing, same way you can prove it. So uh, so uh, so one another property of ladder operator, or the one of the other. I hope you got this one right. So no problem here. So okay. So there is one more uh, identity as well behind this angular momentum operators. So if you take L square with L plus, this will give you 0. And how this happens, like you can see it, suppose uh, yeah, again you can uh, show this way. So L square you can write it as Lx plus ILy, and you have L square Lx plus I L square Ly. And we have seen from the big right at the beginning of angular momentum algebra, that orbital angular momentum algebra that we just started off our discussion. So there we said that L square, if you take the commutation with any of the component of the angular momentum, so they are individually like 0. So that is why. So you have L square when you act with L plus, that will be 0, and same if you do with L square with L minus, that will also give you 0. So right. Okay. So any problem till this point or anything? So
No, sir.
okay. So no questions. Fine. So okay. So we can see next. Uh, so what we have here, now uh, we are again talking about same ladder operators. So L plus L minus, so again uh, which was defined to be Lx in terms of Lx and Ly. So and if we see them, like if they are defined in terms of Lx and Ly, and Lx Ly, we have also separately expressed in terms of um the theta phi expressions. So if we use the spherical polar expression of the angular momentum operators Lx and Ly, so we can write it them in this way. So yeah. So so this L plus L minus can also be written down in terms of theta and phi expression, uh, just like how we have written Lx and Ly in terms of theta and phi. Using them, we can write down here as well. So if I remind you, so at the beginning, like I have showed you how we can write Lx and Ly in terms of theta and phi operators expressed in terms of theta and phi. in spherical coordinates. So using them, you can write L plus L minus ladder operators. So this is what already given in your question as well. So then it is telling us that if the action of Lz operator, the z component of the angular momentum operator, on spherical harmonics. On spherical harmonics means the this means the uh, LM quantum states or the eigenstates that we were discussing before. So, so if it says that there exists some eigenfunction which is denoted by YLM, and and if I take value of m to be equal to L, so if m is equal to L, then Lz when acts on YLL, it gives us this H bar L YLL, and further, so there are two conditions. So condition one is this, and condition two is if L plus acts on this same YLL, it gives us zero. So so what you have in this question, so you have some information about how L plus and L minus can be written down in terms of theta and phi, in terms of I mean the operators of L plus and L minus can be written down in spherical coordinates in this way. Further, using this using these operators, and also the operator that we know about Lz. So if we use this operator and act it on one function or which is referred to as spherical harmonics, and if we operate it on YLN, then it actually gives us the same YLN with LH bar. So and also if we operate L plus on this YLN, it will give us 0. So then we have to find out what is this Y LL function or the eigenfunction in this case, because it will be eigenfunction of Lz when it acts on Lz. When Lz acts on this function, it gives you the same function back again with some scale factor or the overall factor which we know them by eigenvalue. So the eigenvalue is h bar l. So right. Uh, so we can start off with let's say with Lz. So if you remember, so yeah. So using the first condition, Lz when acts on YLL. So uh, it gives you HLYLL. So, and if you remember, as I have showed you at the beginning, Lz can be written down, this operator, in spherical coordinate uh, to be uh, uh, partial derivative with respect to phi, and then this is acting on YLN, H bar L YLL. Right. So now, so yeah. So if you remember again, I can go back. The Yeah. So these are the three. So Lx is in this way. Ly defined to be this, and Lz is simply IH bar del by del phi. So yeah. So that is Lz for you, and acting on YLN gives H bar L YL, and then here you see this actually forms a ordinary differential equation. So if you see, if I write it as del YLL, this is a uh, it's partial, or this is basically a type of partial differential equation. You have IYLL, right? So yeah, now again you can use your idea about solving differential equation, like how you do in mathematical courses. So the same here also, like if you do simple variable separation right here, uh, uh, Yeah, so again, if you do, so this is something of the form, uh, like when you 1 over something y l l, your variable is dy ll. uh, so this is you are integrating with respect to d phi with some constant. So now remember, this is a like uh, partial differential equation. So for partial differential equation, so this constant that which you will have, it will be function of some, it will be some function of uh, theta. So the one which you are not, so because yl, if you remember yl, as we have said it before, it should be a function of both uh, theta and some phi together, with together theta and phi, some function of theta and phi forms this spherical harmonics. So that is why, so now when we are dealing with partial derivatives of phi, so that means if you solve this partial differential equation just like how you do in mathematics, so you will have the constant to be something of f of theta, not simply a constant value. It should be constant in other variable. So that is what you do in partial differential equation. So again, so if you the solve the partial differential equation, so you will have yll to be yll of theta and phi can be given to be f of theta, uh, and so you will have, yeah, so you can see if you solve this, you will find logarithm of yll, uh, and then like phi right over here. uh, Sorry, so there is iota as well. So suppose if I phi on the right, then plus f of theta. Yeah, so this is what you will get. So then yeah, so then I can write this yl, the solution to be of this form, exponential il phi. uh, so there is also, I have missed it, one more thing here, il. So okay, so so this is simply we are solving a partial differential equation, and then from here, so we got this as our solution right now, and then we will use the other condition which is given to be this one. So now when L plus acts on this YL, it will give us 0. Then it will tell us exactly what is the exact form of f of theta. So right now we have found a form of exact dependency of phi. So which we got it from this condition, the condition 1. So now the exact form of theta on this YLL solution will get from the second one, second condition. So so yeah, again, if anything uh, not you are able to follow, please let me know at any step, or at any step at the beginning, or anywhere, like any uh, I mean at the silliest step also, if you are not finding it or you're finding it difficult to understand, please let me know. So then yeah,
Uh,
Yeah, like
hello,
yeah,
sir.
yeah, yeah.
You have written integration of 1/y and that equation.
Yeah, yeah. Yeah, so integration of 1 by YLL. So yeah, what happened? Uh,
Sir, like you have solved it, like you have made an arrow and then in the blue color you have written ln YLL equals I phi
yeah,
plus
yeah.
f of theta.
This one, right? Yeah, yeah.
Yes, sir. There will be L, right? I L F
Yeah,
L
yeah,
phi.
right, right. There will be L. You are right. So yeah, at the beginning, like I missed an L, so that is why. So that trailing miss of L would be there somewhere in my calculation. So yeah, now, but I think now this is right. So you mean this IL5?
Yes, sir.
Yeah,
Okay.
yeah,
Okay,
yeah,
sir.
yeah, yeah. Yeah. Thanks. Uh, yeah. So yeah, anything else? Like anything, any error if I have done anywhere, or. Uh, or anything which I have not properly able to tell you, or something not you are able to clear. Okay, let me know. So, so next, as given in the problem, so is uh, when L plus act on this YLN, so it will go to be 0. So that means L plus is given as Lx plus ILy. When act on YLN, it will be 0. So, so this means again, if you go back to yeah, now we will use this L plus um, uh, operator, which is already given here. This right here. So we'll take the plus one. So so and one more thing, like why this condition. So this condition is like, even if it is not given to you, so it is understandable, because this condition is bound to follow, because if you are dealing with YLL, so which is something given as LL eigenstate. So when L plus acts on this LL, so it is bound to go to 0, because L is the highest state. So it can only go from L minus L to L minus L plus 1, and so on to L plus L. Yeah, that is our LL. So, so that is why LL. So when L plus acts on LL, it will go to 0. If it would have been Y L minus L, then in that case, so that means L minus L. In that case, L minus could have uh, uh, could have made L minus L to 0, because that is the lowest state. So yeah. So using the form given in the question of the L plus operator, so it is given in this way. Uh, okay, theta plus I cot. Sorry. Yeah. So this is what given in here in the expression for the L plus operator. So I've written in that exact way. So then YLL. So So this YLN, as we have found out here, this will be uh, f of theta uh, exponential IL phi. right, and this goes to 0. So again we'll have some sort of differential equation here. So so again, if you see, if I take the derivative of um, f of theta exponential I alpha, so you will see that like the differential operator with respect to theta will only act on this f of theta. It will not go through exponential I alpha. So that will be something you can treat it as constant. So uh, yeah, so this is sorry, this is uh, let me check. It is given I phi or I alpha. So, yeah, it is I phi. Uh, yes. Just give me a moment. Let me check if the expression is correct or not. Exponential of I of I. Okay, yeah, that is fine. Yeah, so this is correct. So we have this. So now what? Now you have to just like operate this one on here. So so uh, so if you so yeah, you have to operate this on here. So the first differential operator when you will act, so you will find exponential I alpha, because that is just the constant for differential operator del over del theta. So when del over del theta, so here it will only act on f. So and then you have for the second operator, so for the second term of the operator, you have I cot theta. uh, um, so uh, I cot theta will remain as it is. So and you can pull out f of theta as well, because f is again some function of theta, but here we have the derivative operator or the partial derivative operator which is with respect to phi, so it will act on only phi. So that will give you exponential il phi with il factor, and the whole thing is 0 on the right hand side. So yeah, so again you can write something like of this. uh, yeah, again you can have del f del theta, um, del f del theta, and then you have uh, lf cot theta. Yeah, again you can do the same type of uh, uh, integration right here, the same type of differential equation which we have seen here. So the say here also you have that. So it's something like, if you treat it as ordinary differential equation, something you can write it as df over f uh, integral, and on the right you have integral uh, cot theta d theta. So so Yeah, so similarly, so here also the constant which you will get, uh, let me write it here. So here you will have ln f. So if you solve this differential equation, you will get something L of ln sine theta, because if you integrate cot theta, so that is something you will get. And with some constant, let's say that constant is k, and so that is ln f ln sine to the power l. So this is just the logarithmic property. And then finally I have f of theta as something I can write it as, this is some constant, again some other constant, written as a naught uh, sine l theta. So if I take exponential on both the side, so this is what I will get. So yeah, so then f of theta I found it to be this, and then finally I can write y l l theta phi as a naught exponential I l phi. So together this will be this. So this is the final form of y l theta phi. So, as I was telling you at the beginning, also, even if we do not have any idea about uh, YL theta phi expression, uh, like we can start it from the from condition such as this. So we use this to condition to know exactly the form of YLL, and now to get to understand about other. This is we have found out for one specific value of m. So if you see only for m equal to L, so we have found out a solution. But if we want to know what it will be for m equal to minus L, or what it would be for L minus 1, so for that case, like you can operate L minus on here, so it will go to L minus 1. So then you can get the form of or you can get the exact form of y l and l minus 1. So likewise you can go till m equals to minus l. So and after you get all the possible expression of the y lms, taking m from minus l to l, then you can check this from the uh, overall expression which I have showed you at the beginning. So this one. So this expression, now even here also, if you put m equals to L, which we have solved explicitly for that one, so you will find you put wherever in this expression you have m, you put L, you will get exactly the same thing. And also if you use the exact form of PLL cos theta, uh, and here also m will be L, so you will get the exact form which we have found out. So even that associated Legendre polynomial will give you sine L theta if you check for m equal to L case. So yeah. So any problem in this question or anything here? Uh, any doubt? Anything not clear? Uh, like any problem, or any issue you are seeing right here, anything which I might have done incorrect, or something you feel it incorrect, uh, or you are not able to, or probably like I may not able to like properly I may not able to explain you maybe one or two things here exactly well, so you can spot out where exactly I've I'm missing something here. So Okay, so if you are
No,
not,
sir.
sorry, like any question?
No, no, sir.
Okay, fine. So, okay, so we can go ahead and see. So, uh, so we have one more question right here, and it is related with the spin. So, uh, yeah. So yeah, so you have uh, a spin-off particle, and it is placed in a magnetic field, and then the Hamiltonian of that system is given to be minus gamma b sy, or otherwise you can write it to be minus omega sy. So this is basically the energy of the system. So if you this is something again, if you remember from your electrodynamics, I mean some if you recall your basic concept of electrodynamics, if a like any uh, so any like charged particle, if you remember, when it is placed in a magnetic field, so you can express it in terms of the angular momentum. So like the it is given, or probably you will see this more often in the coming topics as well, in nuclear magnetic resonances and further. So this is what the energy of the spin particle inside the magnetic field. Um, so whereas y here given as the y component of the spin operator, and the state of the system, so the initial state of the system is given to be plus. So now what is this plus? So plus is the one of the uh, spin state of the spin half particle. So so again, I think you will know more about the spin half states in detail. So for now, I can tell you that spin, like when you have spin half system, um, a spin-off system, or spin-off particle, if you have a quantum particle of which has a spin half, then it has two states, plus and minus. This is denoted this way, or otherwise this means half, half, and half, and minus half, because that is what it says, that like if you have some state, like yeah, S and ms, then you will have you will have this ms going from minus s to s. So here also you will have half and half, half and minus half. So yeah, this is minus half. Yeah. uh, so again, so if when sz acts on this plus, so if you remember this half, this sms, they are the eigenstates of sz. So that is why when sz acts on plus or minus, if it is plus it means half and half, if it is minus it is half, minus half. So then in that case you have this relation. This is the result. So this is an eigenvalue relation. So again, if I recall you, which I have showed you some moments ago, that when sz acts on ms, sms, so this will give you ms h bar s ms. This is the eigenvalue relation you have. Right. Um, so then this is the so in your question it is given that the spin half particle which is kept in the magnetic field initially had this upstate. This is also otherwise known as upstate and downstate. The plus is the upstate and the minus is the downstate. So initially it has upstate when it was in the magnetic field. So then it is further asked that what is the probability of getting the value of minus h bar by 2. So when the spin was measured after some time, so when the spin was measured after some time t, you are getting the value of the spin. So value of the spin is the eigenvalue has minus h bar by 2. So minus h bar by 2 eigenvalue you will only have if it corresponds to uh, half and minus half step, because only then if you only it means if sz acts on half and minus half, it will give you minus h bar by 2, or otherwise it won't. So if it had been half and half, then it would be the when sz acts on. So measuring the value of sz, it means you are operating sz on half, minus half, or half or half. So if sz acts on half, half, then it would have given h bar by 2 plus h bar by 2. But you are getting minus h bar by 2, so it definitely means the state it corresponds to is half minus half. So, like, was there
Sir,
any? Yeah, is there any question? Right.
sir, uh, can I ask something regarding the assignment given to us in this week, the
Uh,
third assignment?
yeah, in assignment. Yeah, what problem is it?
In the third assignment, there is a question,
Uh,
fifth question, that we have to compute the commutation relation between L plus minus operator and YLM theta phi.
okay,
So
could you tell me a third assignment, third week's assignment? Uh,
yes, it
uh,
is assignment 3,
uh,
fifth question.
Assignment 3
So
fifth. Okay, let me also check here. Let me
yeah,
open right here. Just give me a moment. Uh, is the fifth question is the commutation relation of L plus L
yes,
minus, right?
with YLM theta phi.
Yeah,
Means
violent theta.
my question is that YLM theta phi is basically eigenfunctions, right, of L square and LZ operator.
Yeah, exactly,
So,
right.
how can we compute the commutation relation between an operator and an eigenstate? Means, can we do
Yeah.
that? Means
Uh,
we always compute commutation relation of two operators, but here one is an operator and another one is an eigenstate.
uh, uh,
So that's
right,
a bit
right.
confusing.
Why? Uh, no, it probably means. Uh, Let me check YLM. So, uh, no, you can also treat this YLM as uh, some operators as well, uh, because uh, uh, so like when you have this kind of questions, so like you are right. So that question which you mean is like what, how you are trying to think it is correct. There is no nothing wrong with it. But when if it is given something like L plus minus, you have to check the commutator with y, let's say ylm. So it means that there is something like whenever some commutation is given, you consider some trial function. So this is your trial function. uh, you say that this is your trial function, and then what you do basically, let's say you first want to know L plus with YLM. So you will take L plus and you will act on YLM f of r. So so in this case, it basically means that uh, there is some trial function in which both YLM and L plus are operating on this f of r. So even here also, like if you take L plus acting on YLM f of r, it will basically mean that so okay, so what happens L plus when acts on YLM. Uh, so I think you know that, like when L plus acts on YLM, so it will be basically something, you will find some constant. So there will be some like L L plus one or minus um, like I mean there will be something m minus 1, like I do not remember exactly, times h bar, and then this there is L plus, so it will take at y L plus 1 m. So it will be y L plus 1, sorry, not L plus 1, so it will be y L or yeah, it will be m plus 1, and then this whole thing will act on f of r. So it means that,
So
so
how will I means when I will write this equation,
huh,
this commutator,
huh,
so then how will I expand means okay. So
uh,
here L plus comma YLM will operate on f of r. Okay.
right, yeah.
Okay, so then I have to substitute the expression for L plus. Then I have to write here YLM, and then I have to expand this commutator, and then I will operate on
uh,
f of r.
uh,
And then I will cancel off f of r from both sides, and then I will find the
yeah, you
relation.
just have to know like what happens when L plus acts on LM. So this is only L plus acting on YLM, and also you need to know what happens when L minus acts on LM.
Mm.
This is L minus when acting on LM. Then it means that if you have YLM f of r, when L plus acts on it, so you will get this whole thing,
So it
something
will
of this.
only act on L plus will only act on YLM.
No, then there will be one more term as well. Like you will have this YLM act on L plus f of r, right? And then yeah, and then when you will put this in L plus YLM commutation, so it means it has L plus YLM uh, minus YLM L plus, and this whole thing again acts on f of r. So then from here you will get something like you will find that only the square root thing with like whatever h bar ylm will survive, ylm plus or minus 1, whatever.
Um, Sir, how we are getting this second term L plus
uh,
is independent of R, I guess. Means how L plus is operating on a function of R means radial.
no, like it won't be necessarily r, maybe, yeah, you are right. So it could be f of r theta phi. So like uh, it won't be yeah, it won't be f of r, I think, because like I'm saying trial function, you need to have trial function, like anything, let's say it is something general, f of r theta phi.
Okay, so we have to consider as f of r theta phi all the coordinates, and
Yeah,
then I have
yeah,
to expand
yeah,
the operator that
uh,
commutator, and term by term I have to calculate.
yeah. It happens that like you only need to know the commutation, so you only need to know this thing. So you don't need to know this when acts on f of r. So that actually saves you from knowing exactly what is the expression of f of r theta phi. And if you take this commutation, so in this subtraction it happens that this term will go away. So I mean, not zero, this will cancel out. uh,
Which
so
term?
because
The term
this
which contains
this
f of r.
this additional term which you are getting, because you also have to do ylm l plus also.
Yes, yes,
So
yes.
or otherwise, like you take this here, this basically becomes the commutation.
Okay.
Did you understand? Like, I mean, you have you understand till this point, right?
Yes, yes. I
So
have to operate this commutator
uh,
on a general
yeah,
function of
general,
r theta phi.
yeah,
I have to expand the operator, the commutator, and then I have to individually calculate the terms and then subtract it, and then I
yeah,
will
yeah, yeah, yeah.
find
So
the
what I'm saying,
value of
if you have
commutator.
this, like if you able to write this line, so which is l
Mhm.
plus ylm f of some function, trial function, and then you can write what happens when l plus acts on ylm on this one. So you will get, so this is basically uh, this thing plus ylm l plus f of r, whatever f of r theta phi. And then if I take this on the left hand side, so this becomes commutator on the left hand side. Did you get my point? So, like, let's say, so as I was telling, um, so if I, let me copy this part. So uh, yeah, so I have something this, and inside it I will have whatever the square root h bar uh, yl ylm plus 1 f of, let's say, r theta phi. So this is all f of r theta phi, f of,
And the second term it will be uh, YLM first, and then the second one will be L plus operating on F. The second term of the
yeah,
commute.
yeah, so you have something like derivative operators. So for second term will be uh, uh,
Second term will be uh, YLM. It will be in the first place, and L plus will be in the second place. So that L plus will operate on F.
f of r theta phi, right?
Yes.
Yeah, yeah. So what I'm saying, if you bring this to the left hand side, so this will be L plus YLM F minus YLM uh, L plus F,
F.
and
Yes.
then whatever you have. So whatever you have with F, so this becomes L plus YLM commutator F F. So that means L plus YLM is the result, which is basically this thing, the square root uh, with h bar and ylm plus 1. So this will be the outcome of your commutator.
Okay.
So did you get now?
Um,
Yeah.
I was asking how will I calculate this term YLM L plus F, means L plus operating on F.
Yeah, so you do not need to know that. So that is what I am asking, because you need to only find out what is the commutation. I mean, you need not to know the form of f. If you like, if somewhere, if it is given the exact I mean, if you were asked to calculate what will be the l plus ylm acting on f, then you need to know how what will be the outcome of l plus acting on f. Then in that case, you have to know the exact explicit form of f. But here you are only asked to calculate only this, not the entire thing acting on f. So because here whatever you will get with something f, so you can leave out that f. So whatever you have here before f, that will be the commutator of l plus and ylm. So this is what you were asking, right?
Yes, yes. And another one, can I ask?
Yeah, yeah,
Uh, in question number 3, it is asked to
uh,
prove a relation L square equal to R square P
question
square
number
minus R dot P whole square
3. Okay.
plus I H cut R dot P. So here we need to means find L in terms of its components, means
uh,
if
le-
I write L equal to R,
Let me check the question again. So which question you said?
it is question 3.
Okay, question 3, which is given to be L square equals to R square P square. Yeah, yeah, yeah. What?
So I have to write L as R cross P, and then I have to calculate the cross product,
Yeah, yeah, right. You're.
and then I have to take the square, right?
Uh,
But one thing I'm getting in calculation here, in front of IH cut R dot P, I'm getting an extra 2 factor, means
uh,
that's I can't sort it out, means when I write the components of L, so
okay.
the like x component is ypz
Uh,
minus zpy
ZPY, right, right.
whole square. So when I will expand this, how
Uh-huh.
will I expand? I will write y square pz square plus z square py square minus 2 ypz zpy, means it is, these are operators, so I can't change the sequence, right?
Uh,
Means
okay.
ypz minus zpy whole square, if I means expand it, how will I write? Means it, will it be
Okay.
ypz
What you are
square?
telling? So you are telling YPZ and ZPY.
Yes, it is the x
Y.
component of L operator,
Okay. YPZ minus ZPY. So this is something will be this, right? Uh,
so that will be the x component.
that will be the x component. So let's say we are looking into only the Lx square part. So then from yeah. So from here, what problem you have?
Means so when here in the left hand side I have
Uh,
to calculate L square. So L
yeah, L
square
square.
is basically L dot L.
Yeah.
So
So
it
that will
means
be
that all the
uh,
three components will be squared, right? So it will
yeah, L
be,
square, Ly square, Lz square. You will have.
so the first component will be ypz minus zpy whole square
Yeah, yeah.
plus zpx minus xpz whole square
Right,
plus
right.
xpy minus ypx
Right.
whole. So I
Yeah.
will expand the square terms,
Uh,
and then I will get somehow I will get, means I'm having that problem that in the third time in the third term
okay.
I'm getting an extra 2 factor, means that I'm getting IH cut R dot P, but with an extra 2 factor, because in the square I
Uh,
have, if I expand the square I have 2 YPZ ZPY.
okay.
Now PZ into Z I can't change the sequence, right, because they are operators.
Yeah, yeah.
So I'm writing PZ into Z as like ZPZ
So
minus commutator of Z
you are
and PZ,
telling the two factor is coming in the like
because of
in
that too. Yes,
cross
yes,
term type of term. I mean the
yes, yes,
like YZ, ZX, in those terms you have two factor.
yes, yes, yes.
Okay, but
That I can't sort out. Means
I
how,
think that can be absorbed if you see r dot p square. There is also r dot p whole square term. Like if you see, like there also you will get some two factor. What I feel.
okay.
Uh, then. I
Yes,
mean,
I have to go from left hand side to right hand side, right?
yeah, yeah. What I'm saying that, like, if you calculate L square first, you will get this two factor, overall two factor in x, y, y, z type of terms.
Yes, yes.
And also I'm saying, if you do this r dot p whole square thing also, if you calculate r dot p whole square, there also you will get some two factor in the y, z, zx and xy type of terms. So what happens that, like, this thing may cancel out, like, what I feel. And when you will do L square plus r dot p whole square, then you will not have any kind of overall two factor in the cross term, like all those cross term will go away, like. So what I can see from, like, in my uh, uh, yeah, that I think that is probably you will get, uh, like, let me check this is I like what I'm saying, let's say, if you do L
Yes.
square, yeah.
Yes. Can you tell me one thing, that when I will write expand the square
uh,
ypx minus zpy, so how will I write? I will write as y
uh,
square
uh,
pz square
so,
plus z square py square minus 2 ypz zpy. Will it be correct?
to you are telling expanding this one,
Yes, the x component.
the x component. So okay, so if you
Ypz
uh,
minus zpy.
so yeah, so if you like, if you expand this, like, you will get first y, like, uh, there are also, like, I mean, um, ly square and lz square. So, like, you want to expand each of these,
Yes.
like, what I'm saying that, like, there will be also uh, ly and lz term also. So if you expand all of them, so you will get something like, something of this, let me check, something x square type, something x square, uh, uh, del square, del y square plus del square del z square. Then again you will have something y square, del square, and I think you will have del z square plus del square del x square, and then z square. You will have this kind of terms, and then plus you will have, plus or minus, it depends, you have to check, that they will have 2xy, and del square del x del y. Then you will have something minus 2yz, del square
Yes.
del z, del y. And then you will have 2 zx del square del x del y. So this is something you will get. So you are getting this right. And also, probably you will have more, like, something 2x, uh, del x, 2y del y minus 2z del z. So this is what totally you will have when you will take L square, when you will expand L square. So something this you are getting right.
Yes.
Yeah, then it is fine. Then you also check what you will get if you expand r dot p square. So there also you will get some, like some terms plus 2xy del square del x del y, and then you will have 2yz, del square del z del y. So all this 2xy 2yz. So when you will take L square plus r dot p square, so this thing will cancel with this. So
Okay.
yeah, so you will not have any that additional two factor which you are getting. So so you will not have any kind of cross term uh, uh, type of terms in your expression having overall factor of 2. So you will get rid of them when you will take the sum. So are you getting or any confusion still?
Okay, I will try it.
Uh,
Means
you
try.
got the point, no? Right? Like I mean, that two overall factor which you were telling, so that won't remain, which I can see here. uh, or anything like not got it like from here which I am trying to say, or so I'm saying like I'm able to get got your point, right? Which
Yes, yes.
okay, so yeah, so like if you are still having confusion, like please feel free. Or
Okay, so I can also prove that L square plus R dot P whole square is equal to R square P
yeah, you
square.
can also do that. Yeah, you can also do that. That is equal to r square p square plus r dot p term.
Okay,
Yeah, you can also do that. You can at a time compute L square r dot p square and the same expression. You will end up with r square p square on the right hand side plus the r dot p. You
okay.
can, yeah, you can do that as well. Yeah. So okay. So uh, so any other problem or uh,
Oh, it's okay. Thank you.
okay. Yeah. Yeah. So yeah. Okay. Likewise, if anyone else also have any other problem, maybe in your assignments or anywhere in the course, like you can let us know here. Uh, okay. So if uh, okay, if there's no other questions from anywhere else, like from your assignments or the from the your course topics, like which you are uh, able to access them from your portal. Um, Maybe we can check this question right here. Um, yeah, so like I will try to like go through this like quickly over here. Like probably we may not have enough time right here, so I can give you some. Let me just clear out some space here. Okay, so like in the question we were asked to compute the probability. So the probability such that the final state must correspond to something half minus half. So in that case, suppose like let's say the Hamiltonian, which is given in the question, is uh, okay. So this is your yeah. Okay. This is I have already written it here. The plus state means half half, minus state means half minus half. So the Hamiltonian, if you see, it is given as minus omega sy. So this means sy is your spin operator, and let me tell you the spin operator in spin half representation. It is given as h bar by 2, 0, 1, 1, 0, and sy is given as h bar by 2, 0 minus I and 0, and sz is given to be h bar by 2 1 0 0 minus 1. So then your Hamiltonian is basically, so your minus omega h bar by 2 0 minus 1 minus I 0. So now if you see uh, if you see the initially it in the question it is given that when the spin half was in this Hamiltonian, your state of the system was something given to be plus. So this means it is half and half, and this is the eigenstate of which operator. So this is the eigenstate of sz operator. So if you see the sz operator, uh, in this case, if you calculate the eigenvalue and eigenvectors, let's say if I calculate the eigenvalues, I'm calling it as lambda. Uh, that eigenvalues will have basically it will have these eigenvalues 1 0 and 0 1 are basically will be your eigenvalues, and not sorry, this will be your eigenvectors. Let me just say this will be your eigenvectors, and I'm writing it as x. They are the eigenvectors, and lambda is your eigenvalues. So this corresponding to 1 0 eigenvector, it will have h bar by 2 will be your uh, corresponding eigenvalue, and minus h bar by 2 will be the corresponding eigenvalue for the 0 1 eigenvector. So these are your eigen values. So which means when initially you had this state plus state, which means half and half. So plus state corresponds to this. Let me write this. This is your plus state, and this is your minus state. So when it is plus state, your eigenvalue is plus h bar by 2. Uh, so what I can but if you see in the question, the Hamiltonian was given in not in was given in terms of minus omega sy. So sy, if you see the plus or the minus eigenstate, they are only the eigenstate of sz, so they are not the eigenstate of sy. So if you see the eigenstate of sy, so it would be again something. If I write eigenstate of let's say, let's first write the eigenstate of sy. uh, it will be uh, 1 over square root 2. You just have to calculate the just basically how you calculate the eigenvectors of 2 by 2 matrix. Simply you do that, you will get 1 minus I for this matrix sy. uh, if you do for sz, this way you will get. So if you do for sy, so one you will get 1 by root 1 iota, and the other you will get 1 by square root 2 1 and minus iota, and correspondingly you will have eigenvalue h bar by 2 and minus h bar by 2. So what I can do here is like suppose um, uh, yeah uh, so now what it means that if you are measuring the sz value in this Hamiltonian, so you are measuring the spin of the particle, which is whose Hamiltonian is given by this. So then the outcome is you are getting as plus. So it basically means that if you like, for example, I can, what I'm trying to say, uh, you can write plus, which is basically the eigenvalue of sz, in terms of let me write this as eigenvector of sz. This I can write as some linear combination of c1 phi 1 plus C2 phi 2, where phi 1 and phi 2 are basically your eigenvectors of Sy. So this is your phi 1 and this is your phi 2. So why I'm doing this, like, because your Hamiltonian is given in terms of Sy operator. So if you measure the spin, you will basically get either phi 1 or phi 2, uh, because your Hamiltonian is in this form. But if you are getting something as plus, which means you are measuring for Sz, then it will come as some linear combination of eigenstates of Sy operator, that is phi 1 and phi 2. So this means to understand, to know now what are this C1 and C2. They can be calculated, or C1 can be given as, if I take uh, like uh, uh, conjugate of phi 1 and acted on the both sides of the equation, then I will get what is C1. So if I take phi 1, inner product of phi 1 and plus, then I will have basically phi 1 is something, as I said, this is this. So 1 over square root 2, this will be transpose 1 I, and then 1 0 is basically your plus. So this will give you 1 over square root 2. And again C2, if you take phi 2 with plus, you will get 1 over square root 2 1I. So this is minus I and this is plus I, and 1 0. So again this also you will get 1 over square root 2. So again, so that means psi at t equals to 0, which was given to be plus, this is basically your 1 over square root 2 phi 1 plus 1 over square root 2 phi 2. Now if you want to calculate after t time, after after t time means, like, you will evolve this to psi equal to t, uh, with some evolution operator u of t. So again, if you remember, we have used this evolution operator in our last discussion. I can use this, is the evolution operator on the initial state. So now this can give me something, if you this h is now uh, given to be, if you remember, omega sy, which is given in the question. So I have exponential, uh, or yeah, if I write it down, like, if I will get something 1 over square root 2 and exponential I by h bar, I will have omega sy t acting on, uh, okay, acting on the whole thing, 1 by square root phi 1 plus 1 by square root 2 phi 2. So, like, maybe I'm just like, you can do the same type of operation which we have done last time as well. So that will give you basically, like, uh, so one thing just you have to remember, when uh, so sy when acts on phi 1, it will give you what. So we have seen the eigenvalues, it will give you h bar by 2, it will give you h bar by 2 phi 1, and when sy acts on phi 2, it will give you minus h bar by 2 phi 2. So yeah, keeping that in your mind, so uh, you will get something here, 1 over square root 2 I omega by 2 times 1 over square root 2 minus, or I by square root 2, then plus 1 over square root 2 minus I over t, 1 over square root 2 and minus I over square root 2. Okay, then so this, if you write it down, so your final t equals to t will be something given as uh, cos omega t minus sine omega t. Now we are, if you remember, we are asked like what is the probability of getting minus state. So then the probability of getting minus state, it means you have to take the inner product of these two. So this is the probability. So if you do that, like you will get something sine square omega t, sine square omega t by 2. So like I have done, I've gone through very like quickly. So probably you might have missed something. If not, like I can explain you again one more time. So if you quickly have something that not understood here, like or the problem itself, which I tried to go through quickly. So please let me know, like, or I can also try to explain you maybe next time as well. So maybe we are going over the time. So, but yeah, so this is a bit a lengthy problem. So maybe you can go through once if you are interested in this one. So but similar problem you will see in the coming topics as well. So in nuclear magnetic resonances and the other places. So yeah, uh, but okay. So if not with this, if anything with any other problem that we discussed or any other thing particularly related with this angular momentum topic, if there is any question, you can let me know. Any question or uh, okay, if you are not having, okay, fine. So, okay, so then if you are not having any other question, maybe probably we can stop here and we can meet again. And hopefully, you are like finding this course very helpful. And like, yeah, so please go through the uh, materials shared with you already. There are a lot of things. If you find your, if you can access your portal, you will see them. So solve the assignments as well. So yeah, so any problem with assignment also, please let us know here. We can discuss. And yeah, and also the discussion that we are doing here, please see if anything not clear or having any problems. So we can discuss them. Okay, so for now, if there is no question, we can stop here.